boy. Let's just go over here for a second so we can give a quick explanation of where we're going with this and why this would work. So let's say you have a bar of solid iron, and this is just solid iron, and then you put a magnet in front of it, north and south pole. What happens to this? Becomes magnetized, right? Correct. So, and this is temporary, right? So, this soft iron creates eddy currents, which move through it, which are directional forces. I can't draw them specifically right now because I don't know exactly what they look like, but they're force lines of flux. And we can picture that as, let's say, a dielectric field. So for instance, let's just draw the dielectric field in this magnet. So this is the dielectric plane of inertia, right? This little spot right here in the very center where the two magnets switch polarities, right? And then I'm just going to draw the other one polarity on this side, but then you have from the center where the two poles switch polarity, you have a centrifugal vortexual sort of shape coming out of the center, actually traveling in towards the center. So this is actually momentum traveling in towards the very center of that dot, almost like a black hole. Think of the center of this magnet as a black hole. It's consuming, well, it's not really consuming anything, but it's causing a pressure gradient, basically lines of flux in four-dimensional space-time, or the fluidity of space, to be pushed towards the center of this magnet. And excuse me, what happens if you put another magnet, let's just say this is the same thing, let's go north and south, and if this is another magnet here, when this magnet comes in contact with this magnet, what does it do? Well, it pushes this dielectric plane of inertia over, right? So now all of a sudden the center of the magnet isn't right here in the middle, it's over here. And so when the magnet moves, it comes back. And then it moves right back to its original spot again. That dielectric plane of inertia actually extends outside the surface of the magnet, and it's actually one of the stronger components of the magnet, even though we don't recognize it as such. Most of what we see, so this spring or coil looking thing is the reason why if you take a magnet, you put another magnet here, these lines of force are pushing against each other because the turns of the magnet are actually turning in opposite directions. So they push against each other like two springs. If they're traveling in the same direction, then they match up with each other, and then you get a traction. So they pull towards each other or they push away from each other. That's where the repulsion and the attraction force comes from in a magnet. Now, this is called the dielectric field. What most people are commonly thinking of is the magnetic field. So as we have this counterspatial energy traveling in towards the center, traveling down this specific path of flux in four-dimensional space-time, we've got this roll in the ether. So there's like energy coming in this way, and it kind of hits here, and then it bounces up like this. And it kind of circles back around, and it bounces back up, and it circles back around. And so you get this circle formation of energy traveling something that looks like that. Now this is actually it's a torus, more commonly known as a reciprocating hyperbola. So think of the reciprocating hyperbola as this energy is forcing in here, And these are like a donut that's constantly rolling in on itself. And so a lot of times when we are picking up, say here's a little magnet on a flywheel, now we have, let's say we've got a big bag pickup coil that we're going to pick up in front of, and this is, you know, a bunch of turns of copper. Oh boy, how can I, let's try to make it look like this. Here's a pickup coil on a rotor that's traveling by. Now, this pickup coil is only going to get a small amount of the magnetic energy, the magnetic field. This is, we're calling the magnetic field. So the magnetic field is the reciprocating hyperbola, and the dielectric field is the counterspatial vortex in the center that causes the production of the magnetic field. So when this pickup coil is transferring, let's say, you know, it's out here now, but if this was a coil of copper and it's traveling in front of this magnet, it's only passing through this magnetic field at a small ratio, right? The amount of copper to field is not very high. And it may pick up a little bit of the counterspatial field or the dielectric field, but that's it. So these lines of force, these lines of flux that are four-dimensional space-time lines of force, it's not particles. We're dealing with fields here. So the magnetism has nothing to do with particles. Magnetism is a field. And so fields do some unique things. But where was I? So imagine now we've got that part under, it looks like a trumpet or something. Anyway, this takes place on both sides. The magnetic field would be oscillating in the same direction, similar to this. And there's a few more other lines of force that are going to be associated with this. I mean, obviously, if you have all this whirling, swirling lines of force in four-dimensional space-time, in the ether, as we're going to describe it from now on, if this is causing lines of flux in the ether, we are going to have some other, you know, lines of force in this magnetic dielectric field. So, just a small preface there. Now, let's get back to the thought behind this motor. So, in the middle we have a rotor, and I should try to make it round if I can. It'll be as round as I can get it. That's my Easter egg rotor. Anyway, so the way they have it is they have there's a North Pole here, and there's a North Pole here, there's a South Pole here, and there's a South Pole here. There's a few reasons why I believe this specific orientation might give some unique elements, and why it was welded directly to the core of the frame. We'll get into that in a minute. So as this magnet, picture, just for the sake of this, picture this magnet, you know, picture this full magnet. Okay, so now just like over here, we have a magnet with a dielectric plane of inertia in the center. As it passes by this soft iron core, we've got a pickup coil placed somewhere near the back like this, and that's our output coil. Now, it's my belief that when the magnet passes in front of the solid iron core, it magnetizes this solid iron core through the use of eddy currents or lines of force. And in the process of doing so, it creates another magnet. So let's just, you know, like in this case, That's a good question. I don't know the polarity specifically because I haven't ran this test before, but I will let you know when I do. But so this is going to create another magnet, and let's just assume that that magnet also has a dielectric plane of inertia. And I know this is getting kind of screwy. Maybe I will use two different colors just for so we can see it. Let me find another color. And it looks like all I have is pastels right now. So I got these bright colors. We'll see if we can make it work. So again, we've got our soft iron core, which becomes magnetized by this magnet, giving it in turn a north and a south pole. And in the process of doing so, there's going to be this dielectric plane of inertia, which is going to be pushed backwards upon this orange pickup coil, which is that's my pickup coil. So as this dielectric plane of inertia moves this way and passes through the pickup coil, now we have not only, if this is done correctly, one more thing I forgot to mention on here. So if we're looking at that magnet head on, so if we have a square magnet and we're looking at it like, we'll draw a four-dimensional one. I forgot how to draw a four-dimensional square. Three-dimensional square. Four dimensions would be the tesseract, and I'm not drawing a tesseract, am I? So the face of this magnet, what was I getting at? I lost my train of thought. Let's just say this is the North Pole. I'll get it back in a minute. That's the South Pole. Oh yes, the dielectric plane of inertia, which is the dead center of this magnet, the actual counterspatial. So this actually has a field that is flat as could possibly be, as flat as space could be, but it circles. So it goes like this, and that's a horrible representation, but if we were, I shouldn't have done it like that. We'll do it straight on. So if this is your square magnet, it actually has a line of flux that comes out of it very similar like that. And I believe I can get the mathematics on that, so you can actually do calculations. But this looks like a coil, and so this is energy traveling in towards the center of this magnet on this circular pattern, continuously traveling. But this is flat. Remember, this is as flat as a line. It's as flat as a nickel. It's on edge, you know. So you turn this magnet sideways, and it looks like this, and your lines of force are spinning like this, you know, they're spinning on a flat angle. So this is the front view, this is the side view. So then this dielectric plane of inertia, which is thin and spiraling, could actually be wound in the same orientation as the pickup coil itself. So the orientation of the pickup coil matters. Ideally, you would want the copper to be wound in the same direction as the dielectric plane of inertia, so the lines of force can push much more current down the copper itself. You're using the copper as a path of momentum for the four-dimensional space-time pressure gradient that is the dielectric field. Let me repeat that. You are mimicking the dielectric plane of inertia and the orientation of the coil. Ideally would be wound in the same direction. Again, for all this information, look up Ken Wheeler, and A shout out to Ken Wheeler, uncovering the missing secrets of magnetism. Read his great books. They're great. They help you understand magnetism, dielectric field, and it gives you all the mathematical equations that you can use to calculate the actual size of the coil that you need and the orientation of the dielectric plane of inertia in relation to potential coil size. But so that's what your goal is. If you were picking up the magnetic field, the closer the coil would be, the better. But what's happening is this dielectric field that's coming here is coming at like a spring, and it's pushing into here, and it's moving this dielectric plane of inertia over. So that, and if we were just trying to capture the magnetic field, we could easily just put a coil right up close, and we could picture those, the reciprocating hyperbola. But as you can see, look at the cross section of where these coils intersect. So here's where your electricity is generated. Here's your electricity is generated. Here's your electricity is generated. Here's your electricity is generated. And then obviously only at a few points as it passes through the coil. Here, on the other hand, you have much, much more surface area and much more coil. So you're moving an entire flat pancake of energy directly through that coil. So you're picking up much more energy, but the trick is going to be where that dielectric field is created and where to place the precise pickup coil. Now you can get magnetic film that you could put over this, so you could spin the rotor, and as this pickup coil comes, it would energize this. You could literally see exactly what's happening in that core if you get a piece of magnetic film, and that would be best case scenario for you to calculate where your pickup coil over here should be. And what I mean pickup coil, so this is the thing that comes out of the this is the coil of copper that comes out of your microwave and slides over. Remember, these are solid iron cores, because if this was laminated, we wouldn't get that production of the dielectric field because the sheet's too small. You can't. You need the solid iron. You need this to be a magnet. You can't create it if you have 100 little pieces of small, metal all trying to create. It's not what you want. You're not going for that. But it's not a transformer. This is a pickup coil. Two completely different things. In a transformer, you shouldn't build. Don't get me started on transformers. That's a whole nother video. If you want to stay tuned for my video on transformer design and the appropriate way to control eddy currents as a benefit, stay tuned. Like the video, subscribe, check out some other insights of my thoughts on some of these projects. I hope it helps anyone trying to do the research. Remember, get the book. Ken, I hope I spelled that right, Ken, if that's you. If you watch this, I apologize. There might be an A in there. No, I do think it is this E. Ken Wheeler, uncovering the missing secrets of magnetism. Find that book. It'll help you understand what you're trying to accomplish. Stay tuned for more information. We are going to be testing these hypotheses hopefully in the near future, as soon as I get my new lab completely up and rolling. Stay tuned. See ya. I already shut my shop lights off, but I did want to mention one more thing about the composition of the flywheel. I apologize, there is a glare there. But the composition of the flywheel, he's said it many times, it does matter. And the reason that it matters is because when these two fields are opposing each other, when this is trying to generate a field in this, it needs to not be able to, for one, magnetize this. This is just my understanding of what I would do if I was making this motor. And I would make this out of very similar metal that is used for magnetic shielding, like mu metal or any of those. Usually it's a mixture, or they use thin layers of aluminum, copper, and I believe silver, and small amounts of nickel. I believe nickel is not magnetic either. So if I was going to build this flywheel, those are the materials I would start off with. Non-magnetizing metals that block the magnetic field. So that's your goal. You don't want this field permeating any of this, but you also want it being blocked. You kind of want to strengthen this little baby magnet by making it so that the magnetic field doesn't penetrate into the surrounding environment. You don't want the magnetic field getting away. You don't want it affecting the efficiency of any of the other magnets, because believe it or not, these produce a very large field. You can turn a compass from a foot, or more with some of these magnets. So, there is a field that does affect the other fields. So this rotor needs to be made of a material that is resistant to magnetism. It blocks the magnetic field. So aluminum, silver, they say aluminum and silver, copper and nickel, I would also add to those. I believe those two are what they use in the components of mu metal, but I think that's just mu metal. Look it up. I'm not sure. I haven't done that, looked that up in a while, but check out magnetic shielding, and the same components that you would use for magnetic shielding is what you would make this flywheel out of. Thanks for watching.